Hello, ladies and gentlemen. So we are still talking about motion. We're still talking about the ideas of speed, velocity, acceleration, but now we're taking a look at it in the form of a graph, or in some cases, more than one kind of graph. Our our brains really can generally understand uh, graphs and interpret information from graphs much more easily and quickly than it can a long list of distances and times and things of that sort. And so, graphing the data that is collected about the motion of an object can really help a person to understand what is happening with that motion. Now, at the same time, sometimes our brains can deceive us, and we'll talk about that too. By the time we get through the next few days, you should be able to measure and graph changes in motion, interpret an object's motion from a graph, and describe the characteristics of a motion graph. So let's start. We've got a graph here, all kinds of lines on it. And we typically call this type of graph either a distance time graph or a speed graph. On your notes, I've written distance time graph because more often than not, I find that that is a term that's used a little more often. But in the parentheses beside where it says distance time graph, I would suggest that you write in parentheses speed graph beside that, because that is just another name for the exact same thing, distance time graph. So generally speaking, on a speed graph or a distance time graph, and I really shouldn't say generally speaking, this is pretty much always true, you are going to have on the y-axis, you're going to have the distance. The y-axis, you'll remember, is the vertical axis right here. And then the x-axis, which of course is the horizontal axis down at the bottom, that is going to have your time. As I mentioned a moment ago, graphs just make things easier for us to understand. We can look at lists and lists and lists of numbers, but it's much easier for our brains to really wrap themselves around a more visual depiction of that data. The lines that you see on the graph, specifically the colored lines in this particular graph on this screen, um, these lines represent the motion or movement of an object or the speed of an object. All right, so below that section of your notes there, you'll see a blank graph right there in the middle. And I'm going to ask you to fill in that graph. Here is the data that you are going to use. So here's a table with a whole bunch of times in seconds, a whole lot of distances in meters. Go ahead and pause the video while you fill in on that graph this particular data. All right, so you should have, as you plotted that data, you should have ended up, because you connect the dots after you plot the dots, you should have ended up with a graph that looks kind of like this. So it starts here at 0, at 0, 0, then it goes to 110, and then to 220, 330, 440, 550, 660, 770, 880. You should end up with this nice straight diagonal line. All right, this nice straight diagonal line can actually tell us some important information about the motion of this particular object, whatever it might have been. A diagonal line will actually tell us the constant speed of an object, or that an object is going at a constant speed. So when something is moving at a constant speed, it means that its speed is not changing as we go. All right, it doesn't increase, it doesn't decrease, but it stays exactly the same the whole time. So for instance, if we look at this graph, and we'll look where the first two arrows meet on this line, the line showing the motion of the object is in green, the arrows in red. And if we look at that, we will see that that point meets at a distance of 40 kilometers and a time of 40 minutes. Well, if we do a little bit of math, because we know that distance divided by time gives us the speed, we can calculate the speed of the object, and that speed would be 1 kilometer per minute. Well, if we move up the line a little bit to this spot where the arrows are pointing, and we do 60 divided by 60, we are going to see that that also equals 1 kilometer per minute, just like 40 divided by 40 equaled 1 kilometer per minute. Because this is a straight diagonal line, it shows constant speed. No matter where you go on that line, if you do the math, you will come out to 1 kilometer per minute. Okay, so a straight diagonal line always shows that the object is going at a constant speed. Now, at the same time, we could change the line a little bit. I'm going to put in a blue line. This is not going to be particularly straight because I'm trying to draw it with my finger, which never goes particularly well. But if I put in a line that looks more like this, we would say that this particular blue line is showing an object that is moving faster than the green line. How do we know this? Well, a couple different ways. We could do the calculations, okay? Here's a spot here at 40 kilometers, and if we come straight down, we're at a little over 10. So we can see that the speed is faster than 1 kilometer per minute, all right? We can also tell that because it is a steeper line. So the steeper the line, the faster the object is moving. I could come over here and I could put in well, let's not do green. They already did green. So let's choose a purple line. All right. So we'll do a purple line. This one, again, not very straight, but I'm doing my best. All right, this line here shows an object that is moving slower than either the green or the blue because the slope is not as steep. So therefore, that object is moving much slower. All right. The next thing that we can observe when we're looking at a distance time graph is we can tell when an object has no speed or it's stopped, or we might say it's at rest. And that is occurring when we see a horizontal straight line. In other words, time continues on. We go from 0 to 10 to 20 to 30 to 40 to 50 to 60 to 70 to 80 minutes, but the distance stays the same the whole time. Okay, the distance is always 40. And so we say that an object is at rest when that is true. So in this case, maybe the person has stopped at McDonald's for lunch. It's a really long lunch, by the way, at McDonald's. Maybe it's really bad service. I don't know. So the time is changing. The distance is staying the same. So we know that a diagonal line shows constant speed. How steep the slope of that line is helps us determine the speed of the object. And we know that a horizontal line shows an object that is at rest or has no speed. Take a look at this graph for just a moment. What do you think this graph might be telling us? Well, possibly here at the first part, for the first second, we've got an object that's moving along at 10 meters per second. We know that because it went 10 meters in 1 second. And then all of a sudden this object comes to a stop. And is stopped from 1 second to 3 seconds. So for a total of 2 seconds, that object is stopped. And then over the course of the next second, from 3 to 4 seconds, it all of a sudden moves very quickly from 10 meters to 40 meters. So it goes 30 meters in 1 second, 30 meters per second. Okay, much faster than before, 3 times as fast as a matter of fact. So who knows what was actually happening there? Perhaps somebody was walking along, they stopped to talk to a friend, and then they realized they were late and started running. Who knows? But one thing we do know, and this is something that our eyes can deceive us with, we have no idea whether or not this person walked up a hill, then went across a flat piece of land, and then walked up a really steep hill. Even though it kind of looks like that, a distance time graph cannot tell us the shape of the land. Okay? All it can tell us is the distance that the person went and the time it took to get there. We have no idea what the land looked like. They could have been going downhill the whole time. They could have been walking on a flat surface. They could have been going up, down, up, down, up, down. We have no idea, at least not based on this graph. Keep that in mind because we'll be doing an activity where you will need to remember that. We can also learn about velocity from a distance time graph. In fact, just a recap of the definition of velocity. It is speed in a given direction, so it includes both speed and direction. In this case, line A is moving away from point 0, away from the origin or the beginning spot. So it goes from the beginning spot at 0, 0, and it goes to a little over 2 meters away from the original spot. But then it goes right back again. So the direction changed because it ends up back where it started, because it ends up back at 0 kilometers. So it ends up right back where it started after a time of 60 minutes. And we can see that in line B, where it goes back to a distance of 0. Now, we don't know exactly what that motion looked like. It could have been a curvy line and then back, or they could have stopped on a dime and turned around. We don't really know. We just know that they moved to a distance of a little over 2 kilometers away, and then they went back. Took them this, it looks like they went the same speed both directions, because the slope looks about the same. So take a look at this graph for just a moment. Okay. What does this graph tell us? Well, this one does have a title, so we do need to pay attention to the fact that it is a student walking to the store. Maybe we could say that they walked to the store, which was about 1.5 kilometers away, and took them 20 minutes. And then they were at the store for 20 minutes, from 20 to 40 minutes. So for 20 minutes, they were at the store, and then they ran home afterwards, realizing that their mother was going to be upset if they didn't get home quickly. And so it took them 10 minutes to get back home again, back to point 0. That's just one story that we could use. We could get a lot more creative too. The last thing we're going to take a look at that we can see on a distance time graph is we can see acceleration. All right, we saw constant speed with the diagonal line. We could see whether it was a fast or slow constant speed by how steep the slope was. We could see that an object is at rest when there's a straight horizontal line. We can see that there's a change in direction when an object goes back to its starting point. It goes back toward its starting point, gets closer to its starting point when the distance decreases. And then we can see acceleration. So acceleration, you might remember, is a change in speed or velocity over a specific amount of time, remembering that speed and velocity are just about the same thing, but it's more technically a change in velocity over a specific amount of time. And it's shown on a distance time graph with a curved line. Remember, a straight line shows a constant speed. A straight horizontal line is a constant speed of 0. Okay, it's not moving. And a straight diagonal line is a constant speed. A curved line shows velocity, shows acceleration. The steeper that curve, okay, the faster the acceleration. We can also show a decrease in acceleration. Let's make a blue line again this time. We can show a decrease in acceleration when we have a curve that goes down. All right, that would show that the object is actually slowing down. All right, it is going back to its original point as well. All right, so ladies and gentlemen, I suggest that you grab yourself 4 colors if you have them available. And that last graph that is on your page, make sure that you don't have to color them the same color as this, but it will just help your eyes to better see and understand what each of these different kinds of lines tells us about what is happening, okay, to an object, using a distance time graph to show that. So go ahead and color that. Make sure that you filled in the graphs along the way. Each section there had a graph. There was one for constant speed, one for stopping or no speed. There was one for velocity, and there was one for acceleration. If you need to go back in the video, feel free to do that to fill those in. Have a good day.